Now, whenever you have time series data available, and whenever we visualize it and analyze it, the moment we look at a plot, you'd come to know on whether there's a trend component or seasonal component or not. Yeah, look at this for example. You have three different varieties of plots that we need to explore. First thing is level. What is level? Level is average, a simple average. Any data that you deal with, you would be in a position to, of course, find out what is the average. That's going to be a simple task. So here there is an average. This black line is all average basically. So we have that. And when it comes to trend, is there any trend in this first plot? No, it's a constant trend. I do not see an increasing or decreasing trend, right? And do we have any seasonality? Do we have regular up down fluctuations? No, we don't have a regular up and down fluctuation. Hence, it is non-seasonal. And when you look at the second plot, there is a level, no doubt, and in all the plots we have level here. And when it comes to trend, seems like there is a linear trend. Linear is a straight line, of course, linear trend, and there is an upward linear trend. So there is some trend. And when it comes to seasonality, we do not see a regular up-down motion in the data pattern. Hence, there seems to be like there is no seasonality. Now, if you look at the third plot, there is an upward trend, but when it comes to the upward trend, it is slightly exponential. Right? So we have an exponential upward trend, but do we see any seasonality in the data? No. Seasonality means there has to be up-down curve at regular intervals. We don't see that. And we have something called as third order polynomial trend. Right? Here also we do not see any seasonality. What is this exponential trend and what is polynomial trend? I'm going to explain about these two. Yeah. Using Tableau, I will demonstrate that for you all. Now, if you look at the second column of plots that we have, in all these four you have level. Level is simple average, so level would be there as a component. If you look at this first plot here, you see that there's a constant trend. There is no upward or downward trend, but there seems to be a seasonality component. See that there is a regular up-down movement. Seems like there is some seasonality. What is additive seasonality? We'll discuss that later on. Now, in this second plot, multimodal, yeah, there is an upward linear trend. You see that there is an upward linear trend with seasonality once again. There is seasonality. Here also there is an upward trend with seasonality, and this is exponential trend basically. This is exponential trend, and yeah, here also I see that there is some kind of seasonality going on. And we have third order polynomial trend with once again some seasonality. Now, when do we call seasonality as additive or multiplicative? Here, if the magnitude of seasonality doesn't fluctuate drastically, it is additive seasonality. Here also the magnitude doesn't change. Here also the magnitude doesn't change. If the magnitude doesn't change, it is called as additive seasonality. But if the magnitude also changes along with the seasonality, then it is called as multiplicative. Here if you see, the difference is you have a constant seasonality. Here the magnitude is increasing. Here also the magnitude is increasing. Like waves, right? Waves on the sea, beach, you know, the magnitude increases. And that is the difference between additive and seasonality. And why did we discuss that? We have discussed because we know that the data has to be segregated into level, trend, seasonal, and your random component. Once you forecast all these components, you have to combine. When you want to combine, would you use additive technique or would you use multiplicative technique? Right? And when do we actually use it? In order to understand that, we have discussed about additive seasonality and multiplicative. We use additive technique if the magnitude of seasonality doesn't increase, and we use multiplicative seasonality if the magnitude increases. So do you have any doubts until now? Now look at this quarterly sales of ice cream data that we have. And look at this data and comment on what are the various things that you notice here. Do we have a level in this data? What is level? Level is average. Exactly, level is average. Right? So for any data, you will anyways have average. So level would by default be there. So you need not even think twice before answering that. Level will be there in any data. Yeah. Do you see a trend here in this data? Yes, there is an upward trend, absolutely. So there is a trend component also. And is there seasonality in the data? If yes, just explain me about seasonality. What seasonality do you notice here? Additive seasonality, perfect. Can you just quantify it up and down? Yeah, but from the business perspective, from this quarterly sales of ice cream perspective, what do you want to comment? In quarter one, ice cream sales is very less. In third quarter, it increases. In the first quarter, it decreases. Third quarter, it increases. First, third, right? That's the best part. So we have seasonality also in the data. So you have level, we have trend, we have seasonality in the data. So we have all those four in the data basically. When you have cross-sectional data, we have discussed yesterday that cross-sectional data is a data which is collected at a single point of time. And time series data is data which is collected based on time sequence. Given that context, if you have data which is cross-sectional in nature, right, here the data that we have is cost of maintenance versus age of the bus. As in how your vehicles become old, the cost of maintenance would increase. That's given basically. And when you have that kind of cross-sectional data, we tend to use scatter plot. Age of the bus versus cost of maintenance. Right, this is how we plot. And we know how to infer. There is an upward trend. There seems to be clusters. This seems to follow a linear relationship. Strength seems to be strong. All that is fine. But how would you plot if time series data is given to you? If time series data is given to us, then we need to ensure that we plot time on the x-axis and whatever be the variable of interest on y-axis. So you have power usage on y-axis and you have time on x-axis. And you have plotted this. Say we have plotted electrical power usage for Washington Water Power from 1980 to 91. Look at this data and let me know on whether we are going to have level or not in the data. Do we have level? Yes. By default, any data will have level, so you need not even think twice before answering that. Do you see a trend? Overall. What is trend? Trend is overall. Overall increase or decrease. So overall, do you see an increase or decrease? Seems like, right? Slight increase. I mean, if we focus to a great extent, then you might feel that there is a slight increase. Not drastic increase, but overall there is slight increase. So maybe there is an upward trend maybe. And how about seasonality? Do you see seasonality in the data? Yep, there is seasonality in the data. What is that seasonality? Can you quantify? Additive seasonality, perfect frame. because magnitude is not increasing drastically or decreasing drastically. But can you quantify that seasonality? Look at what data is being plotted. We have the electrical power usage for Washington Water Power from 1980 to 91, and you have the quarterly data. So given that context, what do you want to comment? Or qualify the data rather. Not quantify, qualify the data. If you look at this data, do you feel that in Q1 power consumption is increasing, high, and in third quarter it is reducing? Kind of. So this is first quarter. Electricity usage is very high. Once again, Q3 it is low. Q1 high, Q3 low. So this, yeah, alternate quarters, right? Every alternate quarters you see that seasonality. So every Q1 you know for a fact that there will be high electricity usage. Every Q3 there will be low electricity usage given various reasons. So the moment you do this simple time plot, you get to know on what are the various components which are available in your underlying data. And the same strategy employs. If I give you historical data for forecasting, you need to decompose the data, forecast for each component, and combine that. So you need to first of all know whether there is a trend component, whether there is a seasonal component in the data or not. You need to identify that. Another plot that you have to visualize even before you proceed with forecasting is called as lag plot. What is a lag plot? A variable, say you want to look, say you're looking at the monthly sales of VCRs. Right? Say you're looking at the monthly sales. Now, what do you mean with lag plot? YT is a current time period. Exactly. If you plot it against YT minus 1, previous time period, that's called as one step lagged. I'll be using the term time period because time period can be a month. If T is month, then YT minus 1 will be previous month. Right? If this is year, this will be previous year. If this is quarter, this will be previous quarter, so on and so forth. This is one step lagged. And you can also have two steps lagged. If you have YT and YT minus 2, if you're trying to plot these two and look at the correlation between, say, today's sales and today's back sales, it's called a two-step lagged. How will this help? So this is how it will be. Say you have the data for 12 months and YT minus 1 means one step lagged. You'll remove the December month here and it's one step lagged. Then you have two step lagged. That is, you remove the bottom 2 months and that's two step lagged. And when you plot it in this way. You look at the correlation between YT and YT minus 1 or YT and YT minus 2, so on and so forth. And say I'm plotting it for YT and YT minus 1, the current time period and the previous time period, or one step lagged. There seems to be a positive correlation. Fine. Given this positive correlation, let me know on whether you can use the previous time period sales to forecast the current time period sales. There's a correlation. There's a correlation between the current time period and the previous time period. Okay. Given this positive correlation, can I use the previous time period to forecast the current time period, given that I'm using the last sample technique? Last sample is just look at the previous value and say that if someone comes to you and says, hey, what will be the sales tomorrow? You'll ask him on what is the sales today. Today it was 2,000 rupees. So tomorrow also it will be 2,000. That's called as last sample. Very, very naive technique, but yes, it is also used. Yeah, Basant says, no, we cannot use. Any other answers? If yes, no. If yes, why? If no, then why? We will need to look into the seasonality. Yes. Okay. So say this YT is December 2015 and YT is December 2014. Okay. Assume that all those things, yeah, you are right. You're right from your thought process perspective. Very good that you're thinking on those lines. But assume that all those things are considered, given that you are plotting YT and YT minus 1. Assume that all those are accommodated for, and then you see this kind of a plot. I'm looking for another answer also. All these answers are right. Assume that all those are accommodated for. Then, and if there's a positive correlation, can I use the previous time period to forecast the current time period? No. Why is it no? Because if I take the previous time period and say that sales, if I look at previous day's sales and say that today also sales will be same, then it will be wrong because there is an increasing trend here. If there is a constant trend, then probably you could have used yesterday's sales and you could have told that, hey, today also sales will be the same. Because there's a constant trend, it makes sense. But if the trend is increasing, and then if you use previous day's sales to forecast today's sales, then this yesterday's or previous time period sales will be slightly less in comparison to the current time period because there's an increasing trend. Give a thought and let me know whether you are fine with this explanation or not. If there is a stable constant line, no increase decrease, then I can use the previous time, I can use the previous time period data point and I can forecast the current time period. That should be fine. But if there is an increasing or decreasing trend, then the previous time period cannot be used to forecast, right? We not do regression. No, regression in this perspective in forecasting will be slightly different. Okay. When it came to a scatter diagram that we have discussed, we knew that to quantify the strength of the scatter diagram, we had looked into correlation coefficient value. Remember correlation coefficient value, or let me go back. If you look at the scatter diagram and if you want to gauge the strength, we looked into small r, which is called as correlation coefficient value. And this ranges from -1 to +1. And if the modulus of r value is greater than 0.85, you imply that there is a strong correlation. Fine. On similar lines, for this lag plot, which is also kind of scatter diagram, we have something called as autocorrelation value, correlation coefficient, similar to that. And this is represented using RK. And here's a formula to solve that. And this RK correlation, autocorrelation value also ranges from -1 to +1. Okay, this also ranges from -1 to +1. And then there is something called a standard error. When it came to our statistical techniques that we have discussed about, standard error was explained using S over square root n or sigma over square root n, right? And standard error estimates what? Variability between the different samples. Mean estimates the variability between samples. Whereas standard deviation, it measures a variability within a single sample. Okay? And thereby you got standard error. Now, question to you all. Since probability associated with a single value was 0, we were looking at confidence interval and the formula was x bar plus or minus z 1 minus alpha into sigma over square root n. Now within this, we know that 95% is a normal condition, basically normal clause. So what was z 95% equivalent to? What is the 95% equivalent to? 1.96, absolutely. Can I say 1.96 is roughly equal to 2? Yeah, we can say that. And what is sigma over square root n? Sigma over square root n is standard error. So can I take out this part and say plus minus z 95% is roughly 2. Sigma or square root n is called a standard error. This is your interval when it comes to time series data. Okay, plus minus 2 standard error. That is where you're getting this from. This is very important, plus minus 2 standard error. Why do we need to know this plus minus 2 standard error? Because we are now going to look at another plot called as ACF plot or Correlogram. ACF plot or Correlogram. And if there is any lag which exceeds plus minus 2 standard error, it is considered to be statistically significant. And here we go. So here we have a plot. This red dotted line is plus 2 standard error. And this one here is minus 2 standard error. And these are the lags. What do you mean by lag? Say I want to forecast on what will be the VCR sales for say September 2016. Lag 1 is August 2016. Lag 2 is July 2016. Lag 3 is June 2016. Yeah. So what are you trying to do by plotting this ACF plot or Correlogram? ACF stands for autocorrelation function. What are we trying to analyze? We are trying to see on which lag is more significant. Is lag 1 more significant to forecast September sales, or is lag 2 more significant to forecast September sales, or is lag 3 more significant? And you have the autocorrelation value here. Remember, this is like correlation coefficient value, which ranges from -1 to +1. And here also it ranges from -1 to +1, right? And you also know this, that when it comes to correlation coefficient value, modulus of R, if it's greater than 0.85, you say that it's a very strong correlation, right? On similar lines, higher this value, better it is. Higher the correlation value, better it is. That means lag 1 is highly correlated with forecasting September sales. That is what it means, right? But if it crosses the plus minus 2 standard error, the red dotted lines, you say that that particular lag is significant in forecasting the next value. Making sense or not? Ask me if you have any doubts in this, because this will be very important. I just forgot what was the last sentence that I told. Okay. So this autocorrelation plot will help us understand on which lag is significant in forecasting the future value. For example, look at this. We have the electricity usage data here. And say you want to forecast what will be the electricity usage for say Jan 2016. And since I have 12 data points, I'm assuming that these are 12-month data. Lag 1 is the previous month, that is December 2015 electricity usage. Lag 2 is November 2015. Lag 3 is October 2015. Lag 4 is September 2015. Lag 5 is August 2015. Lag 6 is July 2016. So on and so forth. You have data until Jan 2015. Right? And you need to forecast for Jan 2016. What month's electricity usage is more correlated with forecasting Jan 2016? If that is my question, what would be your answer? Now there can be multiple also. When will you call a specific lag as statistically significant in forecasting the next value? If any of these blue lines, that is lags, cross the plus minus 2 standard error confidence interval. Do you see that December lag is crossing? No, it's not crossing. So December month is not significant in forecasting on the electricity usage for Jan 2016. When you look at November, this November data seems to be crossing. So either way, positively correlated or negatively, either way. If it's crossing that red dotted line, that means it is significant in forecasting Jan 2016, right? On similar lines, September 2015 is also significant in forecasting Jan 2016, and then July 2016 also is significant, and on similar lines June, May also is significant. Do you feel that okay, before that I want to give you all an opportunity. Is this clear? By looking at ACF plot, how to determine on what lags are significant in forecasting the future value. Is this clear? Now, do you see anything weird going on in this data? Okay, so why are we considering this red dotted line is Praneeth's question. So for scatter diagram, how do you determine objectively on what is the strength of the correlation between two variables? In the first four, when we started off this course, right, in fourth session, I believe, or maybe in third session, we have discussed about scatter diagram. Remember that? In scatter diagram, we have also discussed that when you try to plot two variables, you'll get to know on whether there is a positive correlation or a negative correlation. We also discussed about the strength. And when we have discussed about strength, we have discussed that if these data points are falling along the line, you say that there is a strong correlation. But in order to quantify the strength of the correlation between the two variables, we have looked at a measure called as correlation coefficient, small r value. And we have also discussed that this small r value ranges from -1 to +1. And if the small r correlation coefficient value, modulus of that, if that is greater than 0.85, you say that there's a strong correlation between y and x. What does strong correlation mean? Say you're trying to predict adipose tissue based on waist circumference, the same example. What do you mean by there is a strong correlation? That means I can use x to predict y, right? That is what it means, right? So what is the thumb rule that we have taken then? Sorry. The thumb rule that we have taken was if r value is greater than 0.85. On similar lines, if I want to forecast on what will be the electricity usage for the next month, that is r squared, Swaroop. R squared value explains the variation, yeah? That's not r. Okay, here r is different. Now, on similar lines, if there is a good correlation between today's sales and yesterday's sales, can I not use yesterday's sales to forecast today's sales? I can, right? Based on the strong correlation, I can comment. And what should be that strong correlation? There has to be some cutoff, right? Like 0.85, there has to be some cutoff. And that cutoff is ±2 standard error. If the autocorrelation values are autocorrelation value, if this value is greater than +2 standard error or less than less than -2 standard error, you say that there is a strong correlation. And what do you mean by strong correlation? I can use that variable for forecasting. For example, here I see that there's a strong correlation, or this autocorrelation value is very high for the second lag. Hence, the second lag is statistically significant and it can be used to forecast your Jan data. Making sense? There we had used, see there we have used modulus of R, right? Greater than 0.85. You could have very well told that R greater than 0.85 and R less than minus 0.85. Here also we are using the same logic. Instead of 0.85, we are using plus 2 standard error, minus 2 standard error. Making sense, Praneeth? But do you see that there is something weird going on here? Do you think December 2015, say, electricity usage will be more relevant to forecast Jan, or do you think November will be more relevant? The immediate previous month, would that be more relevant in time to forecast, or 2 months back data? What do you think? Normally, based on your general knowledge, December month will be more relevant, right? And I believe October is very close in time to now Jan, so maybe October should have been more significant than September for forecasting what will be the electricity usage for Jan. So do you feel that there is something weird about this representation? Yes, there is something weird about this representation, because every alternate month seems to be significant. So what happened in December? Didn't we have any power generation, or was a power plant shut down, or was there any issue? But every alternate month, how can there be an issue? So there seems to be some kind of seasonality effect going on. Hence, this kind of data is not very significant for you. Hence, we are going to re-examine the data by removing the seasonality. And once we remove the seasonality, that is called as de-seasoning. I'll explain on how to calculate that and all that. And when I plot this, now I got a different representation altogether. And when I look at this data, I just get a sense that the last sample is just about significant to forecast, say, Jan 2016 electricity usage. December 2015 is just about good. So all the plots that we have seen from the start until now, be it time plot or lag plot or ACF plot, are going to answer these kind of questions on whether there is a trend in the data, whether you have seasonality in the data, or are the data random. All these kind of questions get answered the moment we look at these plots. Right? A few more finer nuances and then I'll stop for the day. If you look at this plot, this is the hurricane data since 1990 onwards. Yeah. By looking at this data, I get a sense that there are fluctuations. I mean, the trend is increasing, decreasing, increasing, and decreasing, so on and so forth. There is a random pattern. This is yearly data if I plot for each and every year. If I change the x-axis and if I just alter it a little, I will get this kind of a representation. And this is giving a wrong picture altogether. This is telling me that the number of hurricanes have increased until 99 and then it has decreased. But reality was something else. So just by altering your axis in this way, you're going to give a different representation altogether. To avoid this problem, what we do is we try to plot the data at whatever granularity we have. For example, if you have data for every second, plot it for every second rather than aggregating and plotting it for every day. Plot it for every second. That will give you interesting insights as opposed to going ahead with this kind of alteration of x-axis. That's one thing. Second, we should not unnecessarily transform the data. For example, here you have time period t and you have output variable y. If you take log of t, the entire representation has become exponential from linear. So unnecessary, unwarranted transformation of data is meaningless. It would not help. And another point from the plot's perspective is that we always have to ensure that the aspect ratio is properly defined. Aspect ratio is height to width ratio. And this should be 0.618 for your time series. So generally aspect ratio, which is nothing but height to width ratio, should be 0.618 whenever you're doing any visualization. And your Tableau, your click view, majority of the top visualization tools ensure that they abide with the aspect ratio. However, if you have the long time series data, aspect ratio should be around 0.25. That is, if you're looking into centuries of data, when do you want to look at centuries of data? If I want to look at the planet evolution, how did the humankind evolve basically? So if I'm interested in that kind of analysis, yes, there will be a long time series data. And if you have long time series data, then height to width ratio should be 0.25. Look at this plot and let me know on whether the data is random, or if you feel that data is represented in some other way, then also please let me know. Looks random? Now let me plot the same data with proper aspect ratio. It's the same data, but the moment you represent that using proper aspect ratio, you will be able to see those interesting insights which were otherwise not available. Right here, suddenly I sense that there is some kind of seasonality going on, right? Additive seasonality. Let me show you this. So same plot, it's the same plot. Let me expand this and try to ensure that there is proper aspect ratio. Look at that, same plot. Now it's giving you different insights altogether. So the moment you adjust the aspect ratio, height to width ratio, which majority of your visualization tools do intuitively, you will get a better understanding of the data. Yeah, and this is aspect ratio all about. Okay, so I will stop here, and I request you all to download Excel Miner. And the moment you download Excel Miner, this is the kind of plot that you would see, or these are the kind of options that you would see. Excel Miner platform. Right, you should be able to see all of these things: time series, data mining, etc. And we'll be using this data from, or we'll be using Excel Miner heavily from tomorrow onward. Maybe you have not downloaded it properly. It's a simple thing. Let me show you. It is Excel Miner downloads. That's it. If you click on that, the first link which you see, solver.com Excel Miner data mining, you need to just click on that and click on get your 15-day trial. Check the agreement, proceed to download. And based on whether it is 32-bit or 64-bit, just download it. Maybe Srini, maybe you can use a cloud version also. But I've just taken that 15-day trial. I've downloaded that and installed. And the moment installation was, if it's just click next, next, next. And then when I've opened Excel, I've found this Excel Miner platform. Just try to explore that. Maybe you have used some other version. Maybe if it's coming in web, probably as Srini is mentioning, Basant, maybe you're using the cloud version. Either way it works, cloud version or that. You just need to copy and paste the data in cloud. Alright friends, just download and be ready from tomorrow onwards. We'll be working on Excel Miner. Alright friends, thank you so much. Let us connect tomorrow at the same time. Bye for now.